It's a pleasure. Our next speaker is Sofia Olhede from EPFL. Sofia is chair of statistical data science. And I guess in the UK community, definitely been also, you still have it on your slide. So you have, prior to your position at EPFL, worked at UCL. You have, I think, many awards, as I could find out on your sort of on your webpage. The probably most prestigious one at the moment is the ERC Consolidator Fellowship. And today you're going to talk about modeling networks and network populations via graph distances. And I'm very much looking forward to your talk.
Thank you. Thank you very much for inviting me. I know how much work goes into organizing meetings, because I used to do a lot of it. And I can imagine doing it online doesn't really cut down on any of the work. So thank you very much. So today I'm going to talk about modeling networks when you observe more than one network. And I should also, as you say, give thanks to the ERC because they funded this work, at least most of it. And I should also acknowledge my two co-authors, Simone Luna Gomez and Patrick Wolf. So we've heard today of networks, but not networks as data. We've heard about people using network structure in order to sort of hang the algorithm on a network structure. But I'm going to talk about the analysis of network and the analysis of more than one network. So just to get the terminology down, I think networks are kind of ubiquitous nowadays. So people know what all the words mean, but just to be sure that we're all on the same page. So a network is just a representation of interactions or dependence between a set of variables. And the set of variables are normally referred to as nodes or vertices. And between the nodes and vertices, we have edges. And the data really takes the form of edge variables, which tell you whether an edge is present or absent. And what we normally wish to do is to model or infer properties of the whole network.
Sophia, my apologies. Yeah. I just came to my attention in the chat that from some participants, they mentioned that you're almost inaudible.
Oh, sorry.
Is there any way? No, I'm just, if you get, I don't know, closer to the microphone. I personally, I didn't actually experience it like that, but I guess other people.
I'm going to change. If you've ever seen Portlandia, you will have seen the people in the Dooley shop who do sort of art with their headsets, but I'm going to swap headset just to see if that improves things. I could also go like this, but I think it's...
Oh, I think it was probably already louder, but let's see how the other headphones...
Normally you get reverberations. Mm-hmm. So can you hear me better now?
I was personally quite fine beforehand, but I'm not sure. I will probably redirect the question to the person who posted it in the panel. Is this now okay? So Benedict Lamkula says it's better without the headset, apparently. Okay. So maybe we stick to that.
Let's do it that way.
Okay. Apologies. I unmute myself now.
No. It's better to say it early on rather than wait and then say I never heard anything, right? So we're going to be talking about network not as a mathematical structure to hang an algorithm on. We're going to be talking at networks as data. And just to make sure we get all the terminology out of the way, we can have weighted networks where each relationship has a measure of importance, or perhaps how many interactions you have. We're not going to have a weight. We're going to have simple network. We can also have a direction to the network. I might send an email to you, and so a relationship exists. Like you might never email me because you're unsocial. I don't know. And then we can also have bipartite networks where we have two different types of nodes. But we're going to stick with simple networks. And the thing to remember is really the concept of the entities that are related, which are vertices or nodes, if you prefer, and the edges between them. And why do people like these descriptions in practical applications? Well, networks arise in a natural way in social media, like in Twitter or Facebook, where we can already see how a network could be represented. It also comes up in biological pathways and circuits. We can have sensor networks, which even have observationals coming as signals at each node in the network. And we have other social interactions, such as political networks. So we're now going to go away from just thinking about one network to think about having multiple networks. So traditionally, is there more comments? I'm going to ignore the fact that the little bar came up. So traditionally, we only have a single network, and then we ask ourselves what generative mechanism could have given rise to this network. But actually, in practice, we observe more than one network. So for instance, I worked at analysis of methylation data sets where you can define them in different contexts. And we were looking, for instance, at modeling survival times depending on methylation. You might have the setting where a person is getting imaged and you ask them to do different tasks, or you might have them come back and assume that as you repeat the experiment, people have a period of habituation or learning. And you might ask yourself, what's the relationship if I get many measurements of that network that I see, which could be based on function MRI or even diffusion weighted MRI if you're looking at tractography. Or you might have a whole population of individuals having a particular disease, and then asking yourself, well, what does a normal network look like, and what does an abnormal network look like? So what you see on the top right-hand corner is just examples of two methylation networks. And you might ask yourself, like, well, is this normal? Is this abnormal? Should I be concerned or not concerned? And here is another example which brings home to the point that it becomes difficult to treat these as like individual nodes, which you pay too much attention to. So if you look at very small networks, you might think, oh, I could just focus in on each of the nodes and do some analysis node by node by node. But this is, again, a sort of a neuroscience network, and there are too many nodes for you to do sort of individual analysis of the network node by node by node. But it's across a whole set of patients, and what you see is the gray network, we sort of think of as a mean network, which I'll explain to you what that signifies in a little bit. And then what you see as the blue and the pink are nodes that are particular, or edges that are particular to that network relative to the gray network. So you might, and they're kind of a good example because the blue are sort of nodes, edges that connect nodes where the edges are present and added, while the pink are subtracted. And the sort of the difficulty of sort of trying to visually assess the impact of these networks is that if you draw a network that has more than 5 nodes, anything looks like spaghetti bolognese, right? You just shove the pasta down and it's all over the place. So how can I make sense of what's similar or different as I go across the different instantiations? And like networks are definitely not like vector observations. So the question is, what can you do in this setting? Well, let's introduce a little bit of notation so we can try to tease out what we mean by the different aspects of the network structure. So we're going to have a graph G, which is going to consist of the vertices and it's going to consist of the edges. So for the neuroscientific example, the vertices might be a labeling of the different regions of the brain, and the edges could be inferred from fMRI having similar functional activity, or diffusion weighted MRI if you want to see if there are tracts that can be made to connect them. And we think of the edges, the connections, as being the observational units in the data, and most models regard the set of vertices as common and fixed through the whole set of observations, and the edges at random. And often the simplest models we could think of just add edges at random, perhaps with some probability alpha, which is like in the Erdős-Rényi model, where each edge is deemed independent. Or we could have a latent variable, which we never observe, which is Z here. And for each edge between node I and J, we will connect with them or not, depending on if I and J are really similar in this latent space, which would correspond to Zi and Zj, in a sense, taking similar values. and that will then affect the probability. So this is all about how we might generate a single network given we have a model. But what if we actually have little n networks, where we think of the whole network as an observational unit? Well, then this is not just going to suffice, and in fact, it'll be quite silly, because various authors, myself included, have shown, even if we're being completely agnostic or non-parametric, if we have one large network, we can already estimate everything we need. So how do we really bring that together with the fact that we now think we have many networks? Is that just going to be so easy then that we can just go straight ahead and do whatever we like, right? Because there's more data. And we're also going to assume that the networks are exchangeable, which means that there is no particular information in the order we observe the networks. So if you have a set of patients who might have a neuroscientific disorder and their brain deterioration is developing over the course of the observation, what I'm going to talk about today would need to be adapted. We're more thinking about the setting where we have a whole population of samples. We might have a population of healthy and non-healthy patients, and we're taking an observation from each person. So now we need to decide what does it mean to replicate a network? How can we get a new network or have a model so that all the networks in a sense have some similarity? And can we compromise between many observed networks to think that we can get a common generation mechanism between them? And can we really think of some edges in the network as being really there or signal, and some edges which we can just think of as being noise? What does this mean? Well, first, the next step I'm going to take after I tell you about what other people have done is we're going to want to develop the analog of a location scale family. What do I mean by location scale? Well, the easiest thing we learn when we first do our first math degrees is all about the Gaussian distribution. The Gaussian has a mean and it has a variance, and the location is its mean, and the scale is the square root of the variance. So we'd like to understand if we can put a similar model so we can have several network observations from one distribution. And there has been some recent or fairly recent work 2 years ago about asking, what do you do when you have multiple observations from one model, like Newman's work, for instance, or Nielsen and Witten. But people have also started to ask, what if I have noisy versions of the network? What happens? And interestingly enough, a lot of the things we already know kind of go out the window. So Eric Kulacik, for instance, showed that if we have one network and it's getting very big, so that classical network analysis will tell you that you get consistency from all estimation methods, you can approximate its underlying generating mechanism by a stochastic block model. All of these things we know no longer hold when we have noisy realizations, when the edges could have been perturbed at random. So what Kulacik has shown is that in that instance, even as the network grows in size, you'll need to have more than one realized network in order to estimate the underlying generating mechanism. And what does it mean to even talk about location scale families in this setting? Well, in general, we would think about having a random variable, taking some value, and then scaling the random variable so that we can sort of think of a whole set of distributions that can be shifted and scaled. But, and here the notion of a graph space, I think is not anything anyone has ever defined formally. It's a concept we've taken because people use it for modeling graphical models. But it's certainly true that you can't just take an observed network, multiply its adjacency matrix by a constant, and then add another constant, because you'll no longer get a network. So now the question comes back, well, what if I have multiple networks? What is even the average network? Should there be a mean? And this is questions people have already asked when they're analyzing statistical shapes, like what's the average of 10 people's liver if you've done tomography or something like that? well, you can't just average because they won't be aligned, and you'll have to rotate them. And there are lots of other actions you have to put on before you can make them as similar as possible before you might do some averaging. And also, even in sort of standard statistical distribution, something like the Cauchy distribution tells you that the mean is not always a great idea. So just imagine we do have a notion of an average network, a mean network, or a representative network. Let's call it G0. And we're now going to look to have a metric or a measure of divergence, which we'll call D. Then we'll need to have a mechanism of proposing models so that the probability of getting something far from that mean is decreasing as soon as the distance increases. And to do that, we need to decide how we're going to compute the distance. So we're now swapping one problem for another problem. We'll need a little bit more notation to do so. So we'll, as usual, look at the adjacency matrix of a network, which is just a huge tabulation of the edges and non-edges between all of the different nodes. And we'll define the standard graph Laplacian by just doing a large matrix from the degrees on the diagonal and subtract the adjacency. So having those choices, we now have to decide on a suitable graph metric. And it turns out that there are many choices, like most things in life. You want one, which everyone agrees on. And actually, people have come up with several. And there is a nice review paper by Susan Holmes, which goes through the different possible graph metric you might want to use. Now, the first choice you have to do is really to decide about permutations. Like, if you have two graphs, now the main issue with graphs in general is that the way they're enumerated doesn't really have an inherent meaning. Like if you have a social network where you have edges between Bob, Pam, and Sue, it really is the same social construct if it's between Bob, Pam, and Sue, or Sue, Pam, and Bob, right? It's the same social interaction. And that comes back to having to represent things. So if you do permutation of the vertices, all the analysis need to remain the same. And this is a very difficult problem in general, because if you want to compare, for instance, the adjacency and do all possible permutations, we instantly see that that does not scale well. So most of the developments in this talk are going to take a sort of cheap way out of this. We're going to assume metrics where we have the same fixed set of nodes. So this is realistic, for instance, if you have regions in the brain, but it would not be realistic in some other settings where you might want to consider one social interacting network, say at Caltech, and you want to compare it to Imperial. That's not going to work because you need to match the students, and then you have all of these permutations. But we're going to assume that we don't have to solve that problem. We're in the application space where the labels have the same meaning. So some common choices of metrics between different graphs. One tries to find the maximal common subgraph, and in a sense, the difference is really consistent in how many nodes did you need to not involve in order to get the maximum common subgraph between two different networks. That's the maximal common subgraph metric. There's the graph diffusion distance, which tries to view the graph not as just an enumeration of all the edges which you put in a matrix, but instead tries to measure how would things diffuse on your graph. And if you have two different graphs, how are they diffusing differently? And then finally, the easiest distance to imagine is just you have the two adjacency matrices, you've assumed you have the same node, so you just take their difference and you apply your favorite matrix norm. So all of these are choices. What Donrat and Holmes tells us is that they make a difference. Donrat and Holmes are not super hot on the Hamming distance because when the graph gets very sparse, you expect to get more zeros than one, but I often prefer the Hamming distance because it's so simple, it's tractable for analysis, and you can see what's going on. Donrat and Holmes also propose an alternative to the Hamming distance based on the Jacquard distance, where you sort of normalize by the overall expectation of the number of ones versus zeros. But to keep it simple, we're going to focus in this talk on using the graph diffusion distance or the Hamming distance. So, okay, so now we've said we're going to have multiple graphs. We're going to fix their vertices. We're going to now think about putting distributions on this. So first thing to realize is we have to put down a few ground rules to make this work at all. So we're going to need to decide on whatever metric we want. And just as a word of warning here, like once you've enumerated the graph, it's actually in a discrete space, right? You can represent it as a long vector of all the possible edges and put in ones and zeros. So at the end of the day, you're not in a continuous space. And we're going to want to have some desiderata because otherwise none of the analysis will make sense. So we are going to demand that the distribution we put on the graphs that we generate is unimodal. It only has one peak. And you might say, oh, life is more complicated than that. And I'm going to return to that a little bit later with an example. But I would also say the Gaussian distribution is unimodal and is quite useful. We're going to have a typical graph, which we called GM, and we're going to require that as the distance from GM, the typical graph, increases, then the density we put on the further away graph has to go down. And if we're at the same distance apart from the mean or mode or typical graph, then we're putting the same probability of observing something that far apart. So it's sort of saying, yes, we could be in weird situations, but we're going to want these ground rules to actually make the distribution work. So that would give us the notion of a location. We also want the notion of a scale, like we have the variance in the Gaussian distribution. So we're going to assume that we have chosen, again, a metric, and then we're going to consider families which have a second parameter. We're going to call that gamma. You can really think of gamma as being related to the variance of the Gaussian distribution. And then we're going to get the whole family of distributions that depend on the second scale parameter. And we're going to calculate the entropy of the graphs you get. And to make the analysis work, we're also going to assume that we get a strictly monotone function of that entropy as we change the value of the entropy. So again, at the back of your head, you can think about Gaussian distributions. They have a mean, they have a variance, and you can make the distribution very peaked, making the variance very small. You can make the distribution very flat, making the variance very large, and gamma has a similar purpose. So given we have this sort of wishes before we start to do analysis, like a mathematician will instantly ask me, okay, you say you want these things, but are there any models which give them to you, right? Because I could also say I want free rent for the next year or something, right? You can wish for many things, but does this actually have any distributions that satisfy these constraints? And the simplest possible way we could generate multiple graphs, which were slightly different, is simply to flip. So we flip some edges into non-edges and some non-edges into edges. And we can do this independently across the graph and have a probability of flipping. And we call this the centered Erdős-Rényi model because it is like an Erdős-Rényi, except it's flipping from a given graph. It's not flipping to create the graph, it's just modifying the single given graph. And we have a constraint, namely that we assume that the probability of flipping edges to non-edges or non-edges to edges mustn't be bigger than a half, because if that takes place, the notion that the graph is the mean or typical of the distribution that you get out is no longer reasonable, right? So you need to limit that. And this is just an example of what you might get. The red is what we put down as our typical or average graph, and we can just flip edges and get independent realizations like the top row. And in fact, if you have two different graphs that are generated from this distribution, if alpha is less than or equal to a half, then in fact you do have these properties of a well-defined maximum to the distribution, and that things decay as you go away from that maximum. And it's neat in this setting to sort of choose to combine the notion of a centered edges Renyi graph with the Hamming distance, but we then get the whole distribution, which makes sense, that has a well-defined typical graph, etc., etc. But you might say that's a little bit too naive, right? I mean, just flipping edges to non-edges and non-edges to edges, it's a little bit like making an Erdős-Renyi graph, and hey, haven't the probabilists been studying Erdős-Renyi graphs since Erdős made them up? Well, the second set or family that we're going to make up is where we're still going to have the notion of a typical graph, and we're going to generate new graphs, G, by just putting an exponential in there to make sure we get the positive value for the probability of generating the new graphs. And we're going to call it spherical because obviously if you put in the right choice of phi, you will clearly get spherical contours depending on the distance. This is in fact in the Gibbs family of distributions, which have been used for point process models and in other settings. You have to pick both phi and d right, and you can have identifiability issues if you do it nonsensibly. And we know that the Gibbs family distributions are a little bit difficult because they have a very annoying normalizing constant. But we would also here say that this is not the same as exponential random graphs that are super popular. And the reason why is that we have a well-defined typical or modal network, GM, and we're just making up new networks that are slightly away from it. All of the issues that are normally associated with ergoms are not naturally here because we have this notion of a typical or a modal graph. And it is also a member, and also the centered Erdős-Renyi family that we made up is also an example of the spherical class of network models. And in fact, you can show that these desiderata we had for distributions of graphs to make sense, we get them with the spherical network family too. But to show it, we have to choose a particular distance. So for instance, both the diffusion and the Hamming distance work in the setting. And you get a natural notion of both location and scale, depending on your choice of phi. And you can show lots of things with it. Okay, so I've now said we're going to have populations of networks. We're not just going to have a single network. Then you might ask me, okay, so now you made up the notion of having a population. How do we estimate the typical network that we might have? And we're going to be using ideas from shape statistics here. So in shapes, many of the same problems that we have for networks come up again, and that's like averaging two shapes don't really just give you a shape unless you define a good way of doing the averaging. And the sort of the typical way of doing it is to use the Frechet mean, which is to choose a typical shape which is in the family of shapes. So the distance to all of the shapes you've observed is minimized. And that's what we've written down as the definition. And this can also be used in the set of all networks. And that's nice because shapes, in a sense, are less strongly non-Euclidean. Now I did a double negation there, than a network, right? Because shapes, you can locally map them to something that's nice and smooth, and you might locally make lots of arguments that work quite nicely. But a network is strongly non-Euclidean. You can't really make local arguments to make things just okay. But it turns out that you can actually use ideas such as the mean defined in this way to get a new network as your mean. So just imagine for a while, like if you just average adjacency matrices, you would not get an adjacency matrix, you would get a weighted network out. But if you use this definition and you have observed a set of networks, you'll get a new simple network out. It also turns out that if you take the sample and you let the number of networks increase, then they get you the true Frechet mean of the distribution. It exists. And so it makes sense to define this notion of an average. But how are we going to do inference in more general? We might want to get more than the mean out. So now I will blame my collaborator Simone a bit for this, because I'm frequentist and Simone is Bayesian. But Simone persuaded me that the only way to do inferences in this setting is a Bayesian approach, which means we need to write down the likelihood, what the likelihood, if we have assumed either the spherical or the Hamming distance, is trivial and can easily be written down. And the prior you can choose from basically the setting of how people choose priors for coin tosses in general. So you easily get a form of the distribution, and you have a multivariate network model. The prior is a scaled beta, and you get a number of hyperparameters really, which really has to do with this parameter alpha, which is telling us how we're contaminating our networks. And you can then turn the handle, use the Bayesian machinery, and estimate all of the different parameters in the setting. So alpha is important because it's basically, for instance, telling you in this set of realizations, how much have the networks been contaminated compared to the mean. And you can also get a posterior typical network. Just to show you how the mechanics work and like what the structures are, we're first just going to see a simple example where the common nodes are the 19 most frequent mutated human cancer genes. They have higher than expected interconnectivity with respect to genes selected at random. And we're going to put in N1 to N3, a network inferred from expert opinion, experimental determination, and text mining. And we're going to use another as a prior to sort of have the mean sort of gold standard network obtained via co-expression, and then do analysis to see what comes out on the other side. So just to show you first, these are the first networks, N1, N2, N3, and N4. When Simone first showed these to me, I was quite upset because I didn't like the fact that we had multiple isolates, that's 16 or 15, 16, 17, 18, 19, that are not connected to any other nodes in the network. But actually for the machinery, isolates doesn't make a difference. So normally people censor data sets and they throw all nodes away that are isolates. But if you're trying to estimate things like the probability of having an edge, that's not a good idea because you're throwing away lots of zeros that are actually there, they're informative. And having done so, what we get out is a valid network, which is a simple graph, which can be considered the average of those three networks. So this is the main advantage in that the estimated typical network of all these networks is still a real network, a simple graph, rather than just a weighted adjacency matrix. Okay, so that's a little bit too simple. It's good to show because you can see all the different nodes. But what about something meatier where the number of nodes, capital N, is bigger? So we're now going to look at the Connectome data sets, and people use it to find associations between brain structure and function. It's used to describe brain structure and to correlate brain structure. And it's more interesting because, in a sense, all the variables get larger. So the data set we've looked at consists of 300 instances. So we have 300 networks. And the measurements are obtained from both healthy individuals and non-healthy individuals. And we have not 18 nodes, we have 200 nodes. And of course, again, for the vertices to map across, in this setting, we need to actually register the vertices, but that we've used standard methods to do. So I showed you this briefly before, just as an example of a setting where we have more networks. The gray sludge that you see on the bottom right is the modal network. Again, it is a real network because the output of the analysis will give us the typical network as a network. And then you see that here are just three networks picked at random in the set of the 300 data sets. You see that the number of removed edges and added edges, the blue and the pink, where the pink are the removed, are about the same fraction. There's no particular region of more connections or lack of connections, but you're getting sort of a valid notion of changes happening across each individual realization. To do that, we had to use a choice of metric, and we used not for this one the Hamming distance. We tried that as well. We got about the same answers, but we were interested in using the diffusion distance because that's usually representative of thinking information goes through a network, and we want to say that two networks are similar if the same sort of diffusion of information happens. We also, because our methodology relies on having just one peak, we also explored to what extent there was clusters in the data. We basically did some multidimensional scaling analysis, and there wasn't really evidence that there were multiple clusters in the data that we needed to take account of. So that one has not come out so well, but it shows you what happens when you change the name of a slide set. Things can jump around. We also, of course, get analysis of the probability of having the swap between edges and non-edges, which you see at the top, which is alpha. And then we also have basically, we have to worry that this is not too large because it would not be realistic if some of the networks had many, many of the edges swapping. So to sort of put context around this, shape theory and understanding observations, which cannot just be seen as simple numbers that are Gaussian IID, has driven a lot of development in statistics of the past 10 to 20 years. Shapes are considered to be mildly non-Euclidean. You can always think of making little patches on shapes where you don't really have to worry about staying on the shape or not, because they kind of behave all right locally. But whether you're analyzing networks or trees, it's not so easy anymore because they're strongly non-Euclidean. It becomes more important in this setting to stay within the space of networks, because otherwise you might estimate things as something totally crazy, rather like a shape where the mouth didn't connect into one shape or something like that. As we get more than one network, we need to acknowledge the fact that they're not the same network. And in fact, if we expected them to take exactly the same value, why would we take the time to collect them, right? So the only reason you take many observations is because you expect to have some difference, and we need to acknowledge how that variation can happen while still remaining part of the common generative mechanism. And that's kind of what inspired us to go out from having one simple parametric model, like a standard network model, like a latent space model, and go and say we just get many realizations of it. Well, the problem with that is it doesn't acknowledge that you're having variability between the instantiations of networks. And then finally, when we did the modeling, and this really comes in whether we're using the alpha parameter, say for the Hamming distance, to model how many of the edges we flip to non-edges and vice versa, we need to make a choice, right? So we can model GM, the typical graph, as simple or complex, not as a simple network, but as more simple structure, or we can start to worry about the random fluctuation, which is the distribution we put around that mean. Now, this is a choice which happens in statistics in many different areas. It happens in time series where people always assume that you've estimated the mean and chucked it out because you didn't care. But there's also non-parametric function regression where you assume that everything lives in the mean. And the problem also comes up in functional data analysis. So here we've kind of put almost all of the interesting complexity in the mean, and we just want to get the mean back. But it will be interesting to see in the future how these sorts of models develop, just like with the time series, so we can get something like realistic covariances, because we don't really expect an IID-ness in how the nodes behave. The simplest thing you can do is like Kolaczyk, you can put a different probability of swapping ones to zero versus swapping zero to ones. And it's important to retain the sparsity of the network. But how much correlation do you actually want to put in so that you actually end up with whole regions of the network flipping or not? Imagining, for instance, if your network was derived from some imaging activity, if the subject moved, you'd have a whole region which would change its sign or be anomalous. So I think what we will see is people coming up with new, more complicated models that allows complexity in the structure of networks to really come out between observations in the mean or in the sort of the second order structure.